Today we are talking about generalized linear models. What is a generalized linear model? I am so glad you asked. Normally we assume our data are normally distributed. And when our data are normally distributed, or when they follow a normal distribution, we can use probability density functions. And if this is over your head, be sure to visit my video linked in the description on what probability density functions are. But as a quick reminder, remember we use probability density functions to compute things. We use them to compute p-values. We can use them to compute Bayesian p-values or posterior p-values. We could use them to compute confidence intervals, or we could use them to compute credible intervals. All these statistics that we have used in the past are based on the probability density function of the normal distribution. And once again, a probability density function is just a mathematical function that tells us the probability of obtaining a particular range of values. So yeah, we use probability density functions all the time, and we assume a normal distribution. But what happens if the distribution is not normal? Well, let's look at a visual, shall we? So here we have two histograms, or two, technically they're called density plots, that are basically like a histogram. And so we have a normal distribution and a Poisson distribution, and both of them have identical means. So both the normal and the Poisson have a mean of 1. And the proportion of scores that fall beyond that black line is way higher for a normal distribution than it is for a Poisson distribution. And so if you are assuming your distribution is normal when it is actually more of a Poisson, you're going to inflate your probability of a type 1 error. That is bad. And likewise, the width of your confidence interval is just going to be off. It's going to be weird. So basically, what am I trying to say? I'm trying to say that if you use a probability density function to compute these statistics that we need, when your data are not normally distributed, you're going to get into some trouble. So if your data follow a Poisson, you should probably compute your probability density function with a Poisson. Boy, that is fun. That is so much fun to say. Poisson. It makes me sound so elegant and sophisticated. By the way, Poisson means fish, I believe, in French. What does it have to do with the distribution? I don't remember, but maybe I'll look it up and leave a link in the description when I remember. Yeah, basically the idea is you match the probability density function to whatever your data behave as. Now let's step back, big picture. When do we use generalized linear models? Well, obviously we use generalized linear models when our residuals are not normally distributed. But we might also use them when our data are nonlinear or non-heteroscedastic or non-homoscedastic, or when they have heteroscedasticity, which again means non-constant variance. So some examples that you might encounter: maybe you're trying to predict death from heart disease. Death is a binary variable. Those residuals are not going to be normally distributed. Or maybe you're trying to predict sexual assault from aggression or from drinking or something like that. Do we expect sexual assault to be normally distributed? I hope not. We expect that most people don't commit sexual assault at all. And then some people commit a little bit, and then some people commit a little bit more, and then you have this kind of tapering off effect. At least that's what I would hope. That's my faith in humanity right now, that people aren't out there doing evil things. How did we get into talking about evil when we're talking about statistics? I don't know. Or maybe you're trying to predict the number of times somebody goes to therapy. Well, there's a large chunk of the population that don't go at all. And there are maybe more, maybe less, I don't know, who go once. And so you wouldn't expect this to be normally distributed. So in these situations, if you have any sort of situation like this where you don't think the outcome will be normally distributed, you should probably be using generalized linear models. Actually, let me take a tangent. This isn't planned, and I'm going to talk about it anyway. So how did this class come to me? Wow, this is really a tangent. But that's okay. It's important, I think. Back when I first started at Rowan in 2016, they told me that I'd be teaching the multivariate statistics class. In most universities you go to, when you take a multivariate statistics class, you're going to be talking about multivariate analysis of variance, or a MANOVA. You're going to be talking about canonical correlations. You might be talking about factor analysis, because technically multivariate data analysis means you have multiple dependent variables. Problem is, nobody uses these models, and a lot of them are really problematic to use. I think using a MANOVA is stupid. And so when I first came here, I said, is it okay if I don't cover the traditional stuff that you would normally cover in a multivariate class? And they said, hey, you are the statistician, you're the expert, you do whatever you want. So what did I do? I sat down, I said, all right, what are the most common models people need to use? Multiple regression, so of course I was gonna cover that. Mixed models, probably. So I'll do that. Generalized linear models. Those are basically the three things that I cover in my multivariate class. Generalized linear models. Do many people use them? No. So why in the world am I talking about generalized linear models? Because they should be used. It drives me crazy when I see a paper where somebody's outcome is the number of times somebody tried to commit suicide. Well, most people don't try to commit suicide. So you're not going to have a normally distributed data set. And yet people analyze these data as if they are normal. Bad idea, you have the wrong model, that's a horrible idea. So if you have data that are not normally distributed, please don't use a regular linear model. It doesn't make any sense. Again, back to why I chose to put generalized linear models in multivariate class, because they should be used more frequently. Sometimes my students think I'm a little crazy, a little kooky, and that I'm trapped in my own head, and that is true. But sometimes I actually know stuff, weirdly, oddly enough. And she said, yeah, I thought you were kind of crazy. And then I went to a conference and somebody was like, hey, we learned about these really cool models that are like really up and coming and nobody ever uses them because they're really cutting edge. They're called Poisson regression models. And my student laughed and she said, first, that's hilarious because Dustin's been teaching those for weeks. And also, they are not new. They've been around for a long time. And just because some dork hadn't heard of them doesn't mean that nobody's ever heard of them. They are used, and they should be used more frequently. Okay, I think I'm gonna get off my soapbox now. Are we good? We're good, we're tight. All right, good. So again, the point I'm trying to make is that you will if you're doing research, you will most likely encounter a situation where you need to use generalized linear models. So buckle up, it's not that hard, you don't need them. Maybe buckle up is the wrong word, but make sure you learn this stuff because it's important. Now, how do generalized linear models work? Of course, you don't need to be able to know enough to be able to program it yourself. If you did, you would be in my position, or you would be writing software or something like that. You don't need to know it to that degree, but you do need to understand basically what's going on so you can make choices when you're actually doing the analysis. Basically, there are three components to a generalized linear model. One is the systematic component. And by the way, you already know what this is. You remember the y equals b0 plus b1 times x plus b2 times z or whatever? That's the systematic component. That is the function that links our predictors with our outcome. So it's exactly the same with a generalized linear model. There is no change there. So you're good. So that's one, the systematic component. Number two is the link function. L-I-N-K, like Zelda's hero, Link. So link is just a fancy-pantsy mathematical function that bends the line. So here's some examples. In one plot, we have y is equal to x squared. Our link function is the square function. In another one, we have square root of x plus 10. So the link function is the square root of whatever x is, plus 10. And then we have e to the 0.1x, and et cetera, et cetera, et cetera. So all these are link functions. And by the way, I've kind of done a shorthand. The x here could represent b0 plus b1x plus b2 times z. That whole thing we'll call x for this purpose. So we might be squaring the systematic component, or we might be taking the square root of the systematic component, or we might be taking the log of the systematic component, something like that. So again, the link function is just some mathematical formula, very much like a transformation, that delinearizes the mathematical relationship between the predictors and the outcome. Because very often we have to non-linearize things. And then finally, we have the random component. And this is what we were talking about before. We assume in a standard linear model that the residuals are normally distributed. Well, we can instead decide the random component, instead of being a normal, it might be a Poisson, or it might be a negative binomial, or it might be a gamma. So here are some example graphics that illustrate different random components. Here is a normal distribution. Here is a Poisson with a mean of 1-ish. Here's a negative binomial. Here's a gamma, and here's a beta. And by the way, you don't have to look at the distribution of your residuals and have to figure out whether it's going to be a Poisson or a negative binomial. You don't have to do all that, mostly. You basically have to think about what kind of data are you modeling to determine whether you're going to do a Poisson, a negative binomial, or a gamma, or a beta. So if we are doing ordinary regression, by the way, ordinary regression or the linear models that we've been doing, those are generalized linear models too. Their systematic component is b0 plus b1. Well, in this example I'm using, I got b0 plus b1 times depression plus b2 times anxiety. So that right there is our systematic component. It's the same as it's always been. What is our link function? Our link function is 1. We just multiply everything by 1, which gives you the same thing. So the link function is implicit in it, and it's there, but we just use 1. And what is the random component? The random component is a normal distribution. So yeah, standard linear model is a generalized linear model, just a special case of it. Now you might be asking yourself, and I kind of hinted at it earlier, all right, we talked about transformations in the transformations video. Now we're talking about a link function. Aren't they the same thing? And they're very, very similar, but they're not exactly the same. So when we talked about transformations, we were talking about transforming the dependent variable itself. But with a link function, we're not transforming the dependent variable, we are actually transforming the predictions. So let's look at the difference. So here we have the log of y, where y is your dependent variable. That is a transformation. When we are using generalized linear models and we are using link functions, and if it is a log, it would be log of b0 plus b1x. So again, the link function transforms the prediction part, or everything except for the e, whereas the transformation transforms everything including the e. So that's the only difference between the two. So if e is included, it's a transformation. If not, it's a link function. And by the way, the computer will do all this for you. So before, if you wanted to do a transformation, you actually had to do the transformation in R yourself. Whereas if you're doing just a link function, the computer does the link function for you, which is super nice. So different distributions have different default links. So here's just a table that shows you some of the basics, at least in R. So for a linear model or standard regression, the link function is the identity, and that is the link right there. We're just taking b0 plus b1 times x, and the distribution is normal. For a logistic regression, on the other hand, our link function is called the logit. And notice we still have b0 plus b1x. That is, again, the systematic component. But now we're applying this funky equation to it. So we're exponentiating it in the numerator and then doing 1 plus the exponentiated version in the denominator. And the distribution that we assume for the residuals is going to be a binomial. For a Poisson, the default link function is the log. And then we have gamma, and its default link, at least in R, is what we call the inverse function, which is 1 divided by the systematic component, or 1 divided by the prediction equation. Although another common one is the log function. And the residuals we assume are distributed as a gamma. So now to the question I know you are begging to know is, which one do I choose? Such a good question. You are so smart. Have I ever told you that? You're just gorgeously smart. Okay, so for a binomial distribution, we call this the logistic. Why do we call it logistic? Because the link function is called the logit. So we just call it the logistic regression, but the residuals follow a binomial distribution. So here's an example in R. I'm going to go into details in the next video, actually using R to show you how to do all these things. But basically, we use the logistic if we have a binary outcome. You died or you didn't. You're married or you're not. You survived a hospital stay or you didn't. You know, those sorts of things. So anytime you have exactly 2 levels of a variable and you're trying to predict that, you're going to be using logistic regression. Now, Poisson. When would we use a Poisson? You would use a Poisson if you have a skewed discrete distribution. Discrete meaning you don't have like 1.5. It's either 1 or 2 or 3 or 4, like the number of kids you have, or the number of anything you have. By the way, Poisson is very often used if we are modeling a count variable. Number of times you go to the doctor, number of times you're late to work, or something like that. So anytime you have a discrete outcome, usually counts, then you're going to use a Poisson distribution. There's some R code just to give you the basics. Again, we're going to go into this in more detail, and that's what an analysis might look like. And by the way, if you are to use these, your dependent variable must be greater than 0. So if for some reason you have discrete numbers that are like -3, -2, but there's no like -2.7 or something like that, but -3, -2, 1, 0, 1, 2, maybe that's the range of your data, or that's the extent of your data, you can still use a Poisson, but you just have to add, let's say I said -3, so you have to add 3 to everything so that the minimum value is 0. So it has to be 0 or greater. What about a negative binomial? Well, that's when it gets a little bit complicated, but it's not really that complicated. So negative binomial, you would use those for count data. So the thing about a Poisson is that it makes an assumption that may not be realistic all the time. It assumes that your mean is equal to the variance. And usually that kind of works for count data, but sometimes it doesn't work. I'm not going to go into details why that's an assumption, but basically the only difference between a negative binomial and a Poisson is Poisson assumes that the variance and the mean are the same. Negative binomial has a different mean and a different variance. That's all there is. And so in fact, they are nested models. I'll link in the video to remind you what nested models are. So with the same predictors, if you're modeling a Poisson or a negative binomial, the Poisson is nested within the negative binomial. That's negative binomial, there's the R code, there's the visuals. Wahoo. Again, I'm going through these really fast because we're actually going to go into detail in all of these when I'm actually doing an analysis in R. So here's a gamma distribution. What is a gamma distribution for? Gamma is good for skewed, positive, continuous distributions. So if I have a continuous variable, so there might be a 7.4 or a 9.78, which means I can't use a discrete one like a Poisson or a negative binomial. In those situations, I use a gamma. So the gamma is default for me if I have a skewy continuous distribution. That's the word I was looking for. But one of the caveats of the gamma distribution is the variables have to be positive and they have to be greater than 0. So sometimes that may require transforming your data. So if you have negative values, you might add like 10 to everything. So it can be modeled as a gamma distribution. And remember, the default link is 1 over x, or 1 over your prediction equation. And so that's important to remember that when you're looking at the coefficients, that those are now reversed. So if you have a really negative value, that's actually really positive on the original scale of the variable. So you'll see an example of me doing a gamma distribution, and I don't remember in my example if I ended up having to transform the data. I might have, because I think the minimum was 0, and I'll show you how to do that if that is what my example is going to have. Another type of model we might have is called an ordered logistic. So it's like a logistic. You're predicting yes or no, but instead of predicting yes or no, you might be predicting high, medium, and low, or first place, second place, third place, fourth place. And so ordered means it is meant for ordinal variables. So if you have categories like political affiliation, it wouldn't make sense to do an ordered logistic because there has to be some inherent order in it. Distribution is not normal. It is distributed as negative binomial. And essentially what you're doing is, let's say you have 4 categories. You're going to fit a logistic regression saying, are you in category 1 or not? Are you in category 2 or not? Are you in category 3 or not? And then I don't think it needs a 4th one, because if you're not in the first 3, then you have to be in the 4th one. So basically, that's what an ordered logistic is it's fitting just a bunch of different logistic regressions to each level of the data and then summing all those equations up. So this is, by the way, a very, 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 very flexible generalized linear model. Very often, if I can't get anything else to work, an ordered logistic will work. So it's kind of like my last option, but it's not a bad last option. So here's an example of an ordered logistic. It requires the mass package and the Pol R, and that's what our predictions look like. So let's just summarize. Here's a beautiful table that y'all can look at to help you decide what sort of generalized linear model you need to choose. I'm not gonna read all this because this video is already too long, but instead I'm gonna review our learning objectives. Number 1, understand when to use generalized linear models. Again, we use them when we suspect our residuals are not going to be normally distributed, which actually happens quite frequently. Number 2, understand the 3 components of the generalized linear model. And again, that is the systematic component, which is just your standard prediction equation. Then we've got the link function, which bends the line, or it doesn't, because you could have an identity link which doesn't bend the line at all. And then we have the distribution of the residuals, or the random component, which is, is it a normal, or is it a negative binomial, or a Poisson, or something like that. Number 3, understand the difference between a transformation and a link function. Again, a transformation is a mathematical function that you apply to the dependent variable itself, including the residuals. And a link function is what you apply just to the prediction equation, or to the outcome variable minus the residuals. Number 4, understand under what conditions you use a negative binomial, a binomial, or a logistic, normal, gamma, etc. You would use a Poisson when you have count data, or a negative binomial if you have count data. You use a gamma distribution when you have a skewed continuous distribution, but remember it has to be greater than 0. And you would use a logistic regression when you have a binary outcome. So that's basically all I have about generalized linear models. We'll see you in the next video where we are going to talk about actually doing these models in R and the beauty and the glory of FlexPlot. Until then, peace out.